Okay. Good afternoon to everybody. Thank you for joining us today. My name is Colton Marchessault. I'm the president of the Vertical Flight Society Arizona chapter. I'm filling in for Carl Runco, who is our deputy program director who put everything together for us today. So we appreciate all of his support in getting this together. Unfortunately, he had a last-minute conflict arise that he won't be able to join us today. So I will do my best to fill in with some quick announcements, and then we'll get started with our featured presentation. First and foremost, we have the upcoming forum in May that is hosted by VFS headquarters. This year is in Virginia Beach, and we strongly encourage everybody to go to VTOL.org to get to our headquarters website to take a look at the event, and certainly encourage everybody to try to attend if you have interest. There's a lot of very interesting topics. I enjoy my attendance each year that I get a chance to go. I don't know how long-lived that'll be, but I will try to go every darn time that I possibly can. It's certainly a wealth of information. Past that, the Arizona chapter has a few local items going on in the near future. Next weekend, in 2 weeks, we will be over at the Commemorative Air Force Museum across the way from the Boeing facility, where we will support the Commemorative Air Force Museum. They bring out a lot of their old aircraft that are both static displays as well as flying displays. They also usually give the chance for anybody who attends to go and fly in one of their two operating helicopters. The first one is typically about a 9 to 12 passenger UH-1 Huey that they've fully restored and is fully operational. And then depending on the capacity of it as well, they sometimes allow visitors to come out and pay to fly in the AH-1 Cobra that they fully restored, and that is a private flight, just you and the pilot. So it's pretty fun. But otherwise, VFS will be there in attendance as part of a STEM day for us, where we get to showcase our flight simulator, where we fly the Apache AH-64 and get to show kids and adults basically what it feels like to kind of fly a helicopter. It's fairly interactive and reactive, and we truly enjoy having it in our slew of assets to enjoy. And then finally, we are actively ramping up our logistics for our next in-person dinner meeting. We currently have that scheduled for April 21st, which is a Monday. For those local to the area, if you are interested, please reach out to us as soon as possible. We will be posting things on our website, which is vfsaz.org. We plan to have everything up a little bit later today on details and information, but we will be holding that event at the Scottsdale Topgolf. The Topgolf portion, of course, is optional if you would like to partake. But otherwise, we will be having a presentation given by Boeing's chief of vertical lift, Chris Spates, who recently spoke at the eVTOL and AVTOL forum back in February. So if you have interest, again, please follow us on our website. Please feel free to reach out to us for contact information, and we would be happy to get you anything and everything that you would be interested in viewing. With that, I think I will actually turn it over to our featured speaker today. Witold Koning is joining us, and we are very appreciative of his time and sacrifice of time to be here for it. So Witold specializes in low Reynolds number flows and rotor performance evaluation and optimization. His work includes performance predictions for the Ingenuity Mars Helicopter and rotor optimization for the Mars Science Helicopter, the sample recovery helicopters, and NASA's Mars Chopper concept. He also serves as the computational lead for the rotor optimization for the advancement of Mars exploration, ROAMX project, a $2.5 million early career initiative project. Witold earned his master's degree in aerospace engineering from Delft University of Technology in 2015 and has been with NASA Ames ever since. He's an active member of both the American Helicopter Society, now formerly known as the Vertical Flight Society, and the American Institute of Aeronautics and Astronautics, or AIAA. And so with that, I will turn it over to Witold.
Yeah, thank you very much, Colton, and I'll be sure to change that AHS to VFS in for our next one. Hey everyone, thank you for joining this afternoon now, and thank you for being here for the presentation on rotor design for Mars helicopters, overcoming aerodynamic challenges for future Mars exploration. During this talk, I'm kind of going to cover what would probably be the last 5-6 years of some of the work that we've been doing at Ames at the on the aerodynamics side of Mars rotorcraft. And I'd also like to acknowledge my co-authors, so Natalia Perez-Perez, Haley Cummings, Ethan Romander, and Wayne Johnson, without whom it would probably we would have progressed as much as we have to date. All right. So the goal, on the outset was really to provide the methodology to optimize unconventional airfoils and use them effectively to optimize rotor hover performance at Mars conditions. I'll go over this by first kind of, introducing why in the first place flying a helicopter on Mars is hard. And I'll only focus here on the aero side of what is obviously a much bigger problem than just aerodynamics. I'll go over the challenges for efficient airfoil performance, and what was Ingenuity's approach to tackle the peculiar regime that we're looking at. And then finally, the strategy that we, have been investigating ever since Ingenuity's success to try and improve airfoil performance, and with that, then naturally also rotor performance. The way we tried to tackle that is with a optimization tool set called ELISA that we developed, and I'll give a brief high-level overview of how this tool was designed, followed by an overview of the airfoil parameterization and optimization, a methodology that we employed, and then finally the coupling of the airfoil to rotor optimization for this particular problem. Given the people in the room today, we'll also go over briefly of what is the completed but also the ongoing efforts that we're doing in terms of validation and verification of our projects and efforts, and then finally I'll finalize with the conclusions. And well, lastly, of course, all of this is really to support missions after Ingenuity's success, in the hopes that we can have more capable and larger Mars helicopters on Mars, such as, for example, this concept rendering of the Mars Science Helicopter Hexacopter. So for those of you that don't know, the density on the Mars atmosphere, this is kind of the mean density of Ingenuity's design condition is around 0.017 kilogram per meter cubed. So we're really talking about 100 times less than on Earth, which is not ideal, of course, if you want to take off. Now, this is partially compensated by the gravitational acceleration being only 1/3 of that on Earth, but it doesn't really get you in a good space. This then naturally kind of makes you want to spin your rotors faster to partially compensate for this lack of thrust that you can generate. And so you're generally looking at high tip Mach numbers. Ingenuity, for example, I think on Mars was in the range of a tip Mach number of 0.7. And for most of the studies that I will present today, we're really looking at increasing that slightly to Mach tip number of 0.8. To give you a slight idea of what that means in terms of the aerodynamic regime, and let's take 3/4 span of the rotor blade here as representative aerodynamics for the rotor, it results in a Reynolds number of around 20,000 at a Mach number then of 0.6. So definitely an unexplored regime prior to Ingenuity. This is then further complicated because really most of the available low Reynolds number research that exists, or at least the 99% of it, is low in the sense of 100,000 and not an order lower, and then naturally low also implying low Mach number, because usually on Earth it means the velocity is much lower. I will also give you a quick feel for what this actually means in terms of the aerodynamic flows, right? Like this is an example airfoil here at angle of attack, kind of an unconventional airfoil that we're looking at. And I just want you to appreciate the size, the scales that are present in the flow, and how different they are to your conventional airfoil at higher Reynolds number flow that we're much more used to looking at. Here the scales can really be easily double-digit percentage of the chord length, regardless of angle of attack. So as I said before, it's kind of an unexplored aerodynamic regime that almost the entirety of the rotor is in. The graph on the slide here shows Mach number on the y-axis and Reynolds number on the x-axis, and it has kind of two. Let me see if I can pull up a pointer here. two regions are kind of indicated. One being the high-speed data region, meaning data here, meaning, where research has been done on aerodynamics. And this really stems from the commercial airliners and stuff that are in the millions to high millions at, transonic Mach numbers. There is a wealth of data available there. And then you also have kind of, an aggregate low-speed data collection of knowledge that really spans a much broader Reynolds number. But then as soon as you start to increase the Mach number, you get away out of that low Reynolds number regime. And for comparison, I added two representative, cases for 3/4 span of, Earth-based kind of small scale, drones, being the DJI Phantom and the SUI Endurance, and just to compare them to what are the stations of Ingenuity, which is basically the collection of dots here, which is where the Ingenuity rotor is expected to operate. So you can really see that both in Reynolds number and in Mach number, we're in a new regime here. So this particular regime has naturally, because of the low Reynolds numbers, huge implications on the airfoil efficiency. And I'm taking the airfoil here as the building block of the rotor. So I'd like to start with that. And the figure here shows maximum section lift to drag ratio on the y-axis versus Reynolds number on the x-axis. And this is a huge Reynolds number range. So we're going from 100 to high millions here. And it's a rather old graph, or I got it from an old journal paper, but it's very illustrative to show some key problems here that we're facing. The first one is a collection of data collected by McMasters and Henderson for smooth airfoils. Smooth here being conventional teardrop-shaped airfoils with a smooth surface. So as you drop in Reynolds number, at some point there's this massive cliff in maximum section lift to drag ratio that can be obtained, and it's around 100,000 range. In contrast, if we look at the rough airfoils, meaning airfoils with a particular surface roughness, you get slightly lower performance due to the increased skin friction, but there is this crossover region where actually the rough airfoils dramatically outperform the smooth airfoils. And that's all because of the ability then of the rough airfoils to trip the laminar boundary layer to a turbulent boundary layer and not have the disastrous effect of basically the separation of the laminar boundary layer prior to any turbulent transition. The most peculiar part in this figure maybe is that the flat plate here is outperforming the smooth airfoils, which kind of gives already a big hint as to what we're going to really look at for enhanced airfoil performance at these conditions. If we now look at the Reynolds number range that we expect for any Ingenuity class helicopter, we're roughly in this box here. And so conveniently, there is no or barely any airfoil data available. I want to make sure that I mention that these smooth airfoils, we're looking at really thick airfoils, probably the most of them, so they're not particularly well suited for low Reynolds number operation, but it does show you the problem that exists here, where some preliminary data shows you that a flat plate is outperforming airfoil shapes that are thought to be better. If we then take a better look at what exactly is happening with the aerodynamics over an airfoil when you cross these Reynolds number regimes, we can kind of get a better picture or a better feel of what's going on, and we can start to really build our strategy of how to tackle the problem at hand, which is laminar boundary layer separation, which is really the primary impediment to high airfoil performance at low Reynolds numbers. The figure here, I've adapted it from Wang et al. Physics of Fluids thing, and all the flow visualizations here are sketches, but they're based on experimental research on a NACA 0012 airfoil. The y-axis shows the angle of attack, but we won't really focus on that too much here. I mostly want to say that we have like 4 distinct regimes for ultra low, low, moderate, and high Reynolds number here. If we look at the high Reynolds number case, you get your kind of classic airfoil aerodynamic operation, right? You have, for example, if we look at mode F, you have a laminar boundary layer coming in, then the tick mark indicates the transition to a turbulent boundary layer, and then you have an attached turbulent boundary layer all the way to the end. That's basically your best case scenario for, I guess, any airfoil today. Then if you push the angle of attack, you can have either a trailing edge or a leading edge separation that you obviously want to avoid. However, if we then reduce the Reynolds number, now you get in the regime, we're probably around the 100,000 level here, where you have the possibility for laminar separation bubbles. So here we have again, so for mode E, we have a laminar boundary layer incoming. The laminar boundary layer then separates prior to any transition. Because of the separated shear layer now is much more susceptible to the growth of Tolman shifting, like amplification waves. You get transition off body, and the transition then increases the mixing, or however you want to argue to it, into a turbulent boundary layer that is then able to reattach, giving you better performance than stalling, but they're not all that great to have laminar separation bubbles. If you then further reduce the Reynolds number, there's a couple of things that can happen. You either have laminar separation, but you don't have transition of the separated shear layer, but instead you get another instability that kind of causes these big vortices to roll up, and potentially after reattaching, you can have a transition into turbulent boundary layer, or you can have mode B going even lower, where you have laminar separation followed by just separation. So you're essentially stalling, and B is really the classic reason why you have a low performance at low Reynolds numbers. Or if you go in the ultra low regime, maybe primarily even lower than what we're looking at today, you can have a laminar boundary layer that stays attached throughout. So I want to briefly talk a bit about, what was the approach that their environment took for Ingenuity. They obviously were aware of these problems, and also were faced with the same issue, saying how are we supposed to deal with this very low Reynolds number, and how can we get efficient airflow operation? So the strategy was to maintain the laminar boundary layer, as long as possible, preferably kind of over the entire airfoil. The figure on the left shows in white kind of the outline of the CLF 5605 airfoil, so Ingenuity's airfoil, CLF being continuous laminar flow, as that was the aim. And I just want to highlight that, given the timeline of Ingenuity, that's, really the only logical choice that could be made, right? That's the way to do it. Be very careful. You get a slender airfoil. Don't push, the adverse pressure gradient too much so that you reach separation. And when we did some, CFD over this airfoil for representative conditions, we still saw that there is, the possibility for some separation near the trailing edge, just to, give an idea of how challenging these conditions are, because we're here at an angle of attack of 1 degree. So that's very, modest, and these Reynolds numbers are just very, very unforgiving for efficient airflow operation. More recently, we took the Ingenuity airfoil and a new optimized airfoil, and we went to Japan, to Tohoku University, who in their Mars wind tunnel are actually able to recreate representative conditions for Mars operations. So I think still to date, they have the only wind tunnel capability that can reach a Reynolds number of 20,000 at a Mach number of 0.6. And next to some other testing, we did some Schlieren imaging, which for the first time ever was, able to confirm that, at many angles of attack, we're still looking at some separation on the upper surface of the CLF 5605 airfoil. So, for example, here you can see, in the density gradient, you can see the separation on the upper surface, but we're at an angle of attack of -2 degrees. And so when we look at the other angles of attack, we can still see that there's some separation, which really then begs the question saying, okay, so, what else is there? What else can we do to try and improve airflow performance at these conditions? So we already said before that the airfoil picture from McMasters and Henderson kind of indicated that a flat plate might be, advantageous to look at. We did look at that, and it's not as advantageous as we might have hoped. But we did look at an overview saying, okay, what strategies can we, think of and can we, work on? Because there is some work with cambered plates showing really advantageous lift to drag ratios. You have corrugated airfoils, discontinuities. Can we trip the boundary layer? There's a lot of, possible approaches here with each their pros and cons, which we kind of, laid out in this paper. A big kind of breakthrough came when we did kind of a validation study, if you will, for our CFD approach, where we explicitly said, hey, we're using overflow, which normally is used kind of in a RANS setup. But here we said, okay, let's just not use a turbulence model. So we're essentially resolving the Navier-Stokes equations, but over a way to coarse grid to call it, direct numerical simulations, or let alone be fully resolved. The figure on the left shows the pressure coefficient versus the chord, and the triangle show Langley results for an Epler 387, and this is at a Reynolds number of 100,000. And what you can see, we did both 2D and 3D. What you can see is that A, the mean pressure coefficient is captured very well, and B, so how do we capture a laminar separation bubble? Because it's the classic shape, right? When we don't have, in effect, a turbulence model employed. The flow field of this particular state, but instantaneous, is shown on the right here, where you can see the shedding of these large, span-wise vortices that slowly grow unstable and then, develop into, growing towards turbulence, if I can say that. The good thing was here that we already knew that the chance for or to get transition in the classic sense of Tolman-Schlichting wave amplifications, it's going to be not happening, or the chances are going to be extremely small at the Reynolds numbers that we look at. So here we see this other instability, and if we can then provoke this kind of separation and reattachment in a meaningful way, perhaps we can improve the airflow performance on Mars. If we look at the cross sections of the flow here, then here we have that same Epler airfoil, slightly different angle of attack, but okay, you get the picture. And so we have the possibility for laminar separation bubbles, governed by other instabilities than just the amplification of Tolman-Schlichting waves. In this case, large-scale instabilities and vortex shedding resulting in unsteady reattachment or only reattachment of the mean flow. The instability develops, here in this case from the separated shear layer. And if we compare that to Ingenuity, then here we clearly don't have the instability, even starting on time for this to be provoked. If we look at a cambered plate, for example, we can then have the benefit of having the separation at the leading edge here, possibly provoking the same instability, and then having, again, time averaged reattachment, in this kind of intermediary state, if you will. And even better, you can have more advanced shapes where you can kind of pivot the airflow away a bit of the separated shear layer, allow the instabilities to develop in the same way as what we saw on the Epler airfoil, and then align the rest of the airfoil with the vortices that are being shed in a way to maximize performance. So pending a true study on the full mechanism of these instabilities, I just wanted to show that the hypothesis of what exactly is happening, right? So here you see a sketch of a flat plate. We have a stagnation point, separated shear layer. Then because of the shear in the layer, the velocity gradient, you get some pressure difference that then kind of can instigate this Kelvin-Helmholtz instability. And once that starts, it becomes unstable, and you get kind of, along your mean trajectory, you get vortex formation, roll up, and these can, in the mean sense of the flow, result in reattachment type pressure distributions. If we take that airfoil that I showed you previously, and we look at the flow field from the CFD, you can kind of start seeing the same effects. So we have a separation point fixed by the sharp leading edge. You have a free shear layer. You get instabilities because of the velocity gradient in the shear layer. You have then large scale vortices being formed further downstream, and you get, in mean flow reattached CP distribution. So that's really, this case is a different type of parameterization, but this is what we're looking at in terms of getting high performance at low Reynolds number conditions. So if we then go back to this, the graph I showed before, I think there's another important aspect here to highlight, because normally when you're experiencing or you're working on something and you find yourself here in flow mode E, so you have a traditional separation bubble, people kind of, outside of the academic purpose of understanding their behavior, you kind of don't want to have a laminar separation bubble, because the separation location is not fixed. It's highly dependent on operating conditions, vibration, surface roughness, etc. Everything that can contribute to the amplification of Tolman lifting waves. And with that, the airflow performance is highly dependent on operating condition. So whenever you find yourself in flow mode E, you will do everything you can to make sure you're kind of in flow mode F, where you have, your on-body transition and attached boundary layer all the way to the trailing edge. However, now we see that, for Ingenuity, we're more or less in flow mode B, and we could go to flow mode D here, with the advantage here that the separation location can now be fixed by a sharp leading edge. And then the instabilities can grow and can be, used to get like time average a reattachment of the flow. So in this case, it does become beneficial to go to this laminar separation bubble, if only to enforce reattachment of the flow. So that being said, this is kind of what started the ROAMX project. So the rotor optimization for the advancement of Mars exploration. We knew we wanted to, further investigate, the provoking of separation and instabilities using a sharp leading edge. We knew that the chance for Tolman lifting wave amplification is extremely low, if at all existent. And under this program, we developed the evolutionary algorithm for iterative studies of aeromechanics, or ELISA in short, to perform the coupled airflow and rotor optimization and investigate, what could we get here with optimal aerodynamic efficiency in this regime. And just because everybody loves it, here is some, again, a comparison of the flow fields of one of these cambered plate type airfoils that we look at, and then compared to, the flow field for a CLF airfoil from Ingenuity. This is a bit at exaggerated angle of attack, just to show you the difference in the flow field. So this is 6 degrees. Yeah. So the optimization code, I'm going to go really in just high level into this. Feel free to, check the reference if you want to have a deeper dive into this. And the code, in its base constituents really consists of 2 consecutive genetic algorithms to perform sequential airflow and rotor optimization. So the airflow optimization part is evaluating sectional performance in overflow, and the rotor optimization is evaluating rotor hover performance with the free wake model in CAMRAD. And the key here is really that the optimal airfoils, the Pareto optimal set, this function of angle of attack, is linked to the rotor optimization to kind of implicitly couple the two to vastly reduce the dimensionality of the problem at hand. Furthermore, if someone wonders like why are you looking only at hover performance, it's in this case, like, you need to keep in mind that Ingenuity's max forward flight speed was around 10 meters per second, compared to a tip speed of roughly, I think from the top of my head, like 170 meters per second. So regardless at what forward flight speed you're looking at, the advance ratio is so low that you're essentially looking at hover. And this was really the primary means for us to say, okay, let's start with attacking the hover problem, knowing that it doesn't constrain us from having the same or better forward flight speed performance than Ingenuity. The ELISA code, all sections of the code work in kind of a multi-objective optimization approach. So we have a variety of objective choices, currently supporting up to 3 objectives simultaneously. For airfoils, this is lift, drag, and thickness ratio. And we also have this kind of pseudo objective of Reynolds number. And for rotors, it's blade loading and rotor power. And also kind of a pseudo objective of density is supported. We developed the ROAMX airfoil parameterization in a way to allow us to kind of study what are efficient ways to parameterize these airfoils, knowing that we might want to see discontinuities, next to the leading edge, maybe also along the airfoil. I won't go in depth of how we built this up, but in this case, we have a camber line, which is basically just the quadratic Bézier curve. And the control point of that is shown in the blue node here. So this can move around during the optimization, as well as the angle of attack to find, to fill in your Pareto optimal set. And then if different varieties of this parameterization allow you also to include conventional airfoils within your solution space. So here you see, an approximation to the CLF 5605 using a ROAMX, 0303 parameterization. And if you really go into the super low end of the Reynolds numbers, you can do, for example, a ROAMX, 7201, where you have the ability to exploit, discontinuities around the profile. And you're getting kind of like a dragonfly, the insect, not the Titanlander type profile. Then if we take a look at what this optimization for the airfoil side of the problem actually looks like, we have a figure here showing section drag on the y-axis and section lift on the x-axis. And this is for conditions found at the tip of our rotor optimization problem. So we're looking at a Mach number of 0.8 and a Reynolds number of 28,000 here. And when we let the optimization continue, you can see the Pareto optimal set developing, of the Pareto front, developing. And what this essentially means is each blue dot here along the Pareto front is a separate airfoil geometry. So each of these white ones are actually sketched out here, so you can see each of those individual airfoil shapes and what they look like as a function of increased lift. And furthermore, the Pareto front really represents here basically each shape for each section lift. And for each section lift, you have the lowest possible section drag available. Then next to the Pareto front, which are only individual design points, we show in green the drag polar for the Ingenuity airfoil. So this is a polar, and we're comparing a polar with with a Pareto front. So it's not entirely a fair presentation, but it does indicate here how big the gap can be in terms of improvements in drag for equal lift. If we then redo this optimization, but now for a different radial station, 3/4 span, we see now that the distance or the gap between the Pareto front and the Ingenuity airfoil has been reduced, but we're still looking at 20% reduction in drag, which is still a huge contributor to more efficient rotor optimization. Rotor performance. Now, before anyone thinks like, hey, this is all nice, but those airfoils look really thin. Yes, they are. We are working with on the outboard side with 1% thick airfoils, and obviously, that's already a challenge. But going further inboard, you need to have thicker airfoils for your blade stiffness. So for the inboard stations, here I'm showing the route. We did the same optimization, but with a third objective being the airfoil thickness. That really then allows you to post-optimization to then filter out a certain thickness that you need and then re-extract the Pareto optimal set virtually at each thickness constraint. So this one is not particularly well developed, but I just want to show you the idea of increasing thickness in this 3-dimensional objective space, going up here to 10% thickness and re-extracting again the Pareto front out of this particular data set. So obtaining the Pareto from the data set is really the key here of the methodology. So we can do that in any way. In this case, we're varying Reynolds number here, and you can re-extract a particular data set. What's crucial here is that we're then coupling the Pareto front, so here shown in dark blue, to a C81 deck. So we're kind of directly placing each Pareto optimal airfoil for a particular selection of thickness or Reynolds number. And then we're just placing the whole Pareto front essentially in a Pareto optimal C81 deck. So each angle of attack entry in a C81 deck is a different airfoil here. So you're not allowed, technically speaking, to vary angle of attack during a particular camera run later on. But since we're looking at hover, we're really expecting the angle of attack to stay constant. And this has the huge advantage that we can inform CAMRAD during rotor optimization of what the lowest drag is that can be attained at that angle of attack. And the only reason this is valid is because angle of attack and section lift here, they remain proportional even though we're looking at a Pareto optimal set here. So then we go towards the parameterization of the rotor, because we now have a way to inform CAMRAD over optimal airfoils. And we parameterize the rotor using a cubic Bezier point curve for the twist and a cubic Bezier curve for the chord. That allows us to get reasonably developed shapes without, going too deep into like tip optimization, for example, that might be, out of the scope of CAMRAD-based optimization. When we then do the rotor optimization, so we say, CAMRAD, you're free to change the plan form and the twist of the rotor, and the airfoil performance is given to you kind of implicitly, knowing that the angle of attack is not going to change within one run with azimuth. Sorry. If we then let the optimization run its course, we can now see, example rotor power versus rotor thrust graph here. And again, in blue, we have the Pareto front. So each blue dot is a different rotor geometry. This is not the collective sweep, essentially. And in green here, in the same way too as we did for the airfoils, we show the Ingenuity rotor here as a four-bladed single rotor. I forgot to mention we're doing everything as a single rotor to make the work a bit easier, especially on the experimental validation side later on. You can see the predicted increase in rotor thrust for equal power and vice versa. And the both CFD inputs here for the Pareto front as well as Ingenuity performance are done using identical CFD in an effort to really try and compare apples to apples here. The rotor optimization for ROAMX was done using a six-bladed single rotor. We set a thrust-weighted solidity to be equal at 0.25, which was a bit, informed by where we think we're going to go for future studies. And this is really what made us very excited, because if we now plot this data and we plot it as function of figure of merit versus blade loading, then now you can see that there is large increases in figure of merit predicted between 12 and 19% here, depending on blade loading. We highlighted here three rotor geometries from the Pareto optimal set, and then for those geometries, we actually generated actual C81 decks, meaning the airfoil stays constant with angle of attack, and then we could run the collective sweeps, showing that they're getting pretty close to the predicted performance when we run a true rotor model. We also manufactured this blade. Here it is a picture. If you're ever at Ames, feel free to come look at it. We have it here. Yeah, we're pretty proud of that. Then the last step that we did, just to get people extra excited, was saying, well, what does this mean? You now have this increase in thrust, you have this increase in, or predicted increase in thrust, predicted increase in figure of merit. What does that translate to in a vehicle? So we did a quick NDARC study for an Ingenuity class rotor. And if we look at hover time versus range in this graph, the green line here shows Ingenuity's 3-minute hover time, give or take, and 1.5 kilometers of range. And if we look at the final ROAMX rotor, we increased that to, slightly over 5 minutes and roughly 12 kilometers of range and everything in between. So that's really the impact here of these, unconventional airfoils coupled in rotor optimization. Currently, the code has been used for the Mars Helicopter and the sample recovery helicopters, and we're excited to see where it gets to in future missions. Quickly, before I round off here, I just want to give a quick overview of some of the verification and validation efforts before you're all going to ask me that. So for the airfoil, we made some pretty, large assumptions, right? And we did some work, of course, along the way to make sure that we weren't doing anything that was, clearly non-physical. But one of the big ones is that we're optimizing using 2D CFD, right? And we have these large separated unsteady flows. So anyone would ask, saying, hey, is that even at all representative of the true, 3D performance of these airfoils? Secondly, we also didn't employ a Thermos model. So we have no way to evaluate if there is actually, maybe the sharp leading edge is triggering a strong enough instability that you might encounter any Tolman shifting wave amplification, and with that, a completely different possible flow field. So to tackle both of those, what we did is from a big range of angle of attacks for both the Ingenuity airfoil and the ROAMX airfoil 3/4 span, we said, okay, let's compare overflow 2D and quasi 3D. And secondly, let's do this both with overflow, but now also let's remove this assumption of the non-existent of small-scale turbulence. And we set up a SpaceX agreement with Imperial College in London, and their PIFR DNS code is able to fully resolve the flow. And they were happy to contribute and are partnering up with us to replicate the entire data set. So they're doing the same angle of attack sweep in 2D, and they're doing the same angle of attack sweep in quasi 3D. And then we're comparing that with overflow in a way to tackle those first two bullet points. It's not published yet. We're working on it, but we're extremely excited that the ROAMX, optimized airfoil, they're virtually all on top of each other for both 2D and 3D, and DNS versus our under-resolved DNS or overflow cases. Secondly, there's no relevant experimental data available. So as said before, we also set up the SpaceX agreement with Tohoku University, and they now moved to Nagoya University, where we did the experimental testing. And this really, all the credits go to the team at Tohoku University, who did an amazing job. It was an incredible experience to be there with them and get the whole experimental setup done in 1 week. And I quickly want to show you the drag polars that are obtained from the force measurements. So on the right figure, you see lift coefficient versus drag coefficient. And the main takeaway here is just that in black, we have the different manufactured models for Ingenuity, and in blue, we have the ROAMX airfoil, and that the delta here in drag for, more or less equal lift range seems to be, well, as expected, we're in the 30% range. So we're very excited about that. Furthermore, the Tohoku team also did pressure-sensitive paint analysis and Schlieren images. So we're hoping, to soon be able to publish all of that. And oh yeah, just to reinforce that all of this was done for a Reynolds number of 20,000 at a Mach number of 0.6. Then for the rotor main assumptions, we modeled it as a rigid blade. So we partnered up with the University of Maryland, who did rotating blade structural analysis for this exact outer mold line in X3D. And you can see kind of the blade buildup that they developed on the bottom left here. And the link to the paper that describes all their analysis in the bottom left. And some of the very cool things that they figured out was that they said, hey, let's move the pitch axis to 40% chord, because that really reduces the peak stresses near the root. And then after they suggested that, they saw that the propeller moment and the trapeze effect are kind of balancing each other out. That meaning that despite this very thin blade and very, very low well, at least very torsional stiffness, the figure of merit predictions were more or less in the same range as we had predicted using our rigid blade analysis. So we, in a sense, got a bit lucky there, and we didn't have to readjust the twist and iterate with this structural analysis. Nor did we have to readjust the thickness at the root, for which we had the capability at the inboard stations. And then lastly, the camera predictions, of course, it's a bit outside of a known regime. So we have set up the full-scale experimental setup led by my experimental lead, Natalia Perez, and she designed the test stand that you see here on the right, which is very tall. That's why we leave the ladder in there. And you see the ROAMX blades mounted on the top there, and it's in the planetary Aeolian laboratory, so a very, very large vacuum chamber, 4,000 cubic meters, if I'm not mistaken. And you can see me and the PI of the ROAMX project, Haley Cummings, in the bottom here, holding the Ingenuity and ROAMX rotors so that we can do an apples-to-apples comparison using our experimental test stand. Testing was completed last week, or maybe last 2 weeks. So we're now, diving into the data and seeing what's upcoming. That being said, I hope I gave a brief introduction of what the difficulties are that we experience in the Mars atmosphere for efficient airflow operation, where you have near certain separation of the laminar boundary layer for conventional airfoils, and what unconventional airfoils can bring to the increased performance at this regime. Then I showed the ELISA optimization toolset, briefly showing the airflow parameterization, optimization, and then the implicit coupling to the rotor hover optimization. And lastly, showing the validation and verification efforts that we have done or are doing to really complete this effort. Last but not least, I just want to make sure that, even though I'm talking here, there have been an incredible amount of people that were invaluable to this project. Not all of them are listed on this slide, but I just want to make sure that all of the, I don't even know, 50 or 80 people that, along the way made everything possible, they're really all to thank for what we have done to date. And with that, thank you so much for your attention, and I'll take any questions.
All right, thank you very much, Witold. So quickly, I'm putting a couple of links into the chat window. If you guys have any questions that you would like to have sent to the chapter in case we can't get to all of them today, you can reach out to us at vfsaz.org, contact any number of our officers, and we would be happy to forward our questions as applicable to Witold. So, Witold, thank you again. If you can't, for everybody who's in the chat room, please use the raise hand button if you would like to ask a question. If you don't want to ask it, please feel to enter it into the chat window, and we can read them off as we sort of receive them. Rick Derez is our first one with a question in here. Rick, if you can unmute yourself, please feel free to ask your question.
Yes, sir. Thank you, Witold. That was really interesting, and I really appreciate the presentation. I've got a bunch of questions. I'll just do one and see if anyone else has questions.
Sure,
I was
thanks.
curious how in the optimization, when you're simulating these low Reynolds number flows that have these transient flow structures, how you ensure convergence for every airfoil geometry that you're simulating to obtain a point on the Pareto front. Like, how are you checking for convergence and ensuring that before you complete that simulation?
Yeah, thank you, Rick. Excellent question. So there's a couple of things. I guess you're first of all, really good question. Obviously, it's a difficult thing to ensure convergence for every single case that we're running, because you're also already looking at what is moderately expensive CFD. It's like depending a bit on how you set it up, 30 minutes maybe for one airfoil and one data point, right? And so we want to minimize that, but we also want to ensure that we converge, and even more important, as you already alluded to, the unsteadiness of the flow. More often than not, we're looking kind of at like chaotic CL time history or CD time history. So it's not at all obvious how you take the mean of this flow to present your data point in the Pareto optimal set. So what we did is I can send you the link. There's a paper out there on how you can kind of statistically determine where the transients of your simulation have ended. That's by no means perfect because I'm not sure you can 100% be sure about that, but at least in the time histories after each generation is completed, the code checks where these time histories are predicted to end their transient part. And then afterwards, it makes sure to, we select, we say, okay, we want to have at least 25 flow passes to make a meaningful average, but that has to fit after that transient point has passed. So that's on the unsteady part. Then for overflow itself, we obviously set the minimum convergence for each time step to either second or third order before it's allowed to go to the next time step, unless, and this is the delicate balance, you have some very odd case where, say, you have some, vertical plate in the flow and it's just like too much. So we try to balance out maximum allowed time steps with, needed convergence. But those are flagged at least so that we know that we're not mispicking or coincidentally grabbing, a fake or non-physical point simply because the simulation didn't converge. That being said, the final step to avoid any of this fuzziness is, of course, when we make the dedicated C81 decks, we run them, full bore, hundreds of flow passes so that we get super meaningful averages, and then we verify that the collective sweep is actually going to the design point from, as inferred from the optimization. So that's, I guess, a couple of layers that we build into to ensure that we're picking the right point, and then even if we think we picked the right point, that as good as we can do, at least in 2D airfoil, that we know we're matching our expected performance.
Wow, thank you. Appreciate it.
Absolutely.
And Rick, we might come back to you. I do have one question from the chat window I'll go to really quickly, and then we can see where we're at after that. This is from Lane. How much does weather or wind on Mars impact the performance of the aircraft?
Okay, good question. I'm not sure if I'm, fully able to capture all the difficulties that come with it. I guess one that might be way more prominent in the first place is already how much the atmospheric density on Mars varies just with the elevation. If you're on top of a volcano or even a valley on Mars, you're really going from, well, the range we're at for Ingenuity to maybe an order of magnitude lower and bordering the level where you even could fly, So before we even look at weather, it's not even a given that you can fly everywhere on Mars just because the density is already so low. Winds can get pretty high, and that's where it gets a bit tricky. I don't think I have a ready answer on how much it will affect rotor performance in terms of like adding unsteadiness to the simulation. But at the same time, the dynamic pressures are so low that the impact of that can be kind of moderate in terms of, that was for Ingenuity, for example, tip over risk or stuff. That's then very low. But yeah, in terms of, how much a wind gust could affect the performance, not 100% sure here. And I guess that's also, the flight dynamics guys that I happily hand over this particular problem.
I don't think I have anybody else with their hands raised, and I don't see any more from the chat. So, Rick, we'll definitely go back to you.
All right, thanks. So my next question, I was curious if for these low Reynolds number regime, when we use a tool like a comprehensive tool like Camera 2, which uses 2D airfoil data and with that like blade element assumption, like recognizing it's still high aspect ratio blades, but I'm curious if the low Reynolds number sort of starts to mess with the assumption of using 2D sectional properties. Does that make sense?
Yeah, absolutely. First of all, another great question. And I have some answers for you. I also don't want to pretend that means that there is not more to answer right here. There is a lot to discover still. the part of course, the main assumption of the sectional performance was really, we were already worried about it because we're looking at such unsteady flow. And because we haven't published it yet, because we're seeing really that it's the same in terms of 3D performance for one airfoil, at least that gives us some confidence that the primary, the primary instabilities remain 2D, even if the flow kind of collapses, right? But to answer the bigger question, I think that you're asking here is really, well, you have multiple of these airfoils, they're different, they're, along the span, how valid is it and what happens when they're next to each other? The big part is that for a big part, we really don't know yet, because we haven't gotten yet to the 3D CFD part, which is, I guess, the one where you really can start to digest the differences between the sectional inputs that you expect and what is exactly happening. That being said, though, we did look at this, of course, for Ingenuity. So for Ingenuity, we do have 3D CFD, sectional performance, or CD1 models. And there, despite the obvious, always existing, questions on where some differences with experimental results, for example, come from, we did see fairly good agreement between CAMRAD, at least on the blade loading level, between what was expected from CAMRAD and, fully 3D CFD. So not a perfect answer. We know from Ingenuity where, despite completely different operating regime of these airfoils, you still have, at certain collective angles, of course, massive separation. You see similar kind of, big vortices being shed, of course, that in part is very much captured by CAMRAD, but you're completely right in that there will be more on the horizon here to explore when we have a data set that we can use to actually answer this question for the ROAMX rotor or any unconventional airfoil along the blade.
Thanks. Yeah, it sounds like the assumption's still generally valid, where you can use 2D sectional data for the rotor, through most of the rotor.
Yeah, exactly. So we have good confidence. It's the 2D assumption at the CFD level is valid, and then it's for me, it's really the bigger mark is like, okay, what happens when you place these different airfoils along the span of a rotor, right? And different instability, growth, etc.
Thank you.
All right, we got about 2 minutes left. There's one more question that popped up in the chat from Lane again. How are the rotor blades fabricated? I'm not sure if that's something you can answer if you touched on earlier.
Yeah, so the University of Maryland, they, after their analysis, we presented them our outer mold line. And we then said, hey, this is our hub, so you're free to modify the inboard section of the blade to however it works best for the structural analysis. So they then provided us with the final outer mold line, and that outer mold line was sent to Sensenich company here in the US, and they were the ones who then made the blade molds essentially and did the carbon fiber layups, etc., and manufactured them. And because they're so thin, really outboard of 50%, it's a 1% thick airfoil. So there's only, there's no space for a spar or anything. So there's just 2 layers of carbon fiber, essentially, there's skin only. And then further inboard, there is a thicker section, of course, including the root here. I hope that answers your question. If it goes much deeper than that, I'm not sure if I can answer the exact manufacturing process, but I'm sure the link of the Maryland colleagues have more details on that.
Right. We are just about at time. John, I saw that you had your hand raised. I'm not sure if you intentionally put it down. Are there any other questions from the field? Okay, I will say perfect timing then. So thank you everybody for your attendance today. And VTOL, thank you very much for your presentation as well as your fielding of the Q&A. I really appreciate your time. On behalf of the Arizona chapter of Vertical Flight Society, again, we could not thank you enough for being here today and for everybody else for your attendance. So again, please feel free to visit our local website, vfsaz.org, for all of our upcoming events as we get them posted. If you need to get a hold of us, please use any of the contact from our executive board page on that site. we'd be happy to answer anything. And if you guys have any outline questions that weren't answered here today, please feel free to forward those to us so that we could pass them over to VTOL as well. With that, we'll adjourn for the day. Again, appreciate everybody's time. Have a great afternoon, and we'll see you next time.
Thanks, everyone.